Good morning, madam. My name is Tan Wei Kwan. My matrix number is B0820103338, and I'm from 2BEI, Section 1, Group 2. Today, I'm going to present, based on our journal, on introduction. Thermal energy storage, short form TES, is considered an advanced energy technology. The use of thermal energy storage system has been attracting increasing interest in several thermal applications, such as active and passive solar heating, water heating, cooling, and air conditioning. Thermal energy storage often is the most economical storage technology for building heating, cooling, and air conditioning applications. The most well-known is pumped hydro storage, PHS, and compressed air energy storage, CAES. Pumped thermal energy storage consists of strong electricity as heat with a reversible heat pump, which has advantage of being site independent and potentially highly cost effective since the storage medium can be cheap with high energy density. The medium could be water, concrete, or other fluids and solids. Okay, on the left side of the slide, you can shown a figure which show cycle points and components shown during charge and discharge. And during discharge, the arrow are reversed and the evaporator is a condensation. On the right side, here you can see the a table of comparison of storage technologies. That's all.
Hello, my name is Brandon James. Today I will explain the basic layout of pump. It's called thermal energy storage (BTS). Okay, this is the diagram and illustration for the BTS. They have evaporator, hot tank, cool tank, point 1, point 2, point 3, point 4. Okay, the working fluid run a thermodynamic cycle with an expander, compressor, heat exchanger, evaporator, or can condenser. The storage fluid flow from the cold tank to the hot tank, receiving heat from the working fluid in between. Working fluid from point 1 to point 2, the work ratio amount of compression work is divided by expansion work performed during charge from point 3 to point 4. A high ratio will reduce the losses in round trip and efficiency due to the turbomachinery and is therefore desirable. The heat storage ratio is the amount of heat storage. And the next slide, field selection for thermodynamic. Any substance that conforms to the shape of its container, it may be either a liquid or a gas. In physics, the field is substance that continually deform flow under an applied shear stress. The working fluid of a heat engine or heat pump is a gas or liquid, usually called refrigerant, coolant, or working gas, that primarily convert thermal energy into mechanical energy by phase change and heat of compression expansion. The majority of these fluids is not suitable for transcritical cycle bottoming at ambient temperature T0 equal to 15 degrees Celsius. Food selection for the thermodynamic is mass following BMID, T critical, mass higher than TO, zero temperature, starting temperature. The cycle is rejecting heat at ambient during discharge, and when a peak rate is lower than 250 bar, the pressure reached in the cycle must be realistically manageable from material point of view. Okay, for the environment, more recent regulation restrict the use of fuel in terms of their global warming potential. Europe Union regulatory guidelines are used here to discriminate between the field is 0 or below around 0.02. For the low, global warming potential is must be below the 150. And the acceptable for wet field is sulfur dioxide, carbon dioxide, ammonia, and ethane. For the acceptable for the dry field is butane, isobutane, isobutane. And for the safety, the working field of the PTS should also be safe to handle because mostly the field is vulnerable, and it should be we must choose with the safeness to be the handle for the working field of the PTS. Most of the selected field is flammable, and the safest one currently used as refrigerant. For example, ammonia, carbon dioxide, R1311, R152A, R161. That's all for me. Thank you.
Salam sejahtera. My name is Patricia Chiloana David. Okay, so today I would like to explain about methodology. For the first one is storage material. As we can see here, this is the table for storage material. Okay, this is for provide low medium range potential storage and also to find particular value at which performance is maximized. Okay, next is compression and expansion. This formula is to find polytropic efficiency. It is 90%. And then for the third one is heat exchanger. Okay, near critical point, heat will vary drastically. Large temperature difference, irreversible entropy. Okay, to avoid these three, we will need to use matching capacitance rate. For the fourth, okay, fourth and fifth is actually connect with each other. Okay, for the condenser and evaporator, this is to find the total efficiency actually for the condenser and evaporator. Okay, for the fifth is charging. Okay, point one is saturated vapor. We can see here this is the graph. So at the point one, it is saturated vapor. At the point two, it is polytropic conversion, and at the point three, there is cooling down. Point four is the same at the point one. So point one depends on temperature difference between evaporator and ambient. Okay, this is the efficiency. So if the efficiency is decreased, so that means the temperature will be decreased. Okay, next is discharging. Okay, discharging actually is the same with charging, but the difference is point four is set as saturated liquid. So for the last one is output. Okay, and the output, okay, we can see the lower heat ratio, the lower total cost per unit power capacity of heat exchanger. This we can calculate it by using HWR. It stands for heat work ratio. Okay, this formula. Then the first formula actually is to find the total efficiency for this thermal energy storage actually. So this one will be compute breakdown exergetic losses. Some wetness or dryness can cause problem because efficiency of turbo machinery reduce. Higher temperature will cause the superheating. Okay, to avoid all of this happened, we will need practical purpose needed. So that's mean we can change the ratio. Okay, because the lower heat ratio, the lower total cost per unit power capacity. That's all from me. Thank you.
Hello, my name is Franklin Umar Adiman from 2 PEI 1/2 section. Today I'm going to explain about summary of finding, which is the results and discussion of the article that we have chosen. Firstly, is on the dependence on top temperature. With increased maximum storage temperature, its fluid loss reduces. Secondly, heat capacity variation and entropy generation are reduced at higher temperatures away from the critical point. As the temperature becomes too high, the losses begin to rise again due to a reduction in the work ratio. Turbomachinery losses reduce as work ratios increase. Hence, at lower storage temperatures, losses are minimal. Work ratio decreases as storage temperature rises and corresponding losses increase. But only carbon dioxide can work with unpressurized water, but its maximum efficiency is at 100 degrees Celsius. Thus, it requires a different fluid or water pressure to around 2.5 bar to operate at optimal point. Secondly is the Pareto France and ranking. The heat to work ratio and power density are also essential, and their temperature dependency is obvious. Thus, with the former decreasing with T2 and the latter increasing, both in a linearly manner, and achieving maximum efficiency, power density, and heat to work ratio is unachievable. Thus, a Pareto front has to be done to describe the fluid's power density and heat to work ratio at optimal operating temperature for the round trip efficiency. The ideal fluid would be at the bottom right corner where the cost of heat exchangers and turbomachinery per unit power is low. They differ greatly from one fluid to the next, with carbon dioxide and ammonia dominating in these areas, but despite having the lowest efficiency of the fluids. This is except for the three wet fluids, where most fluids do not enter the two-phase area during discharge at ideal operating temperature, where it is an disadvantage. Value of P2 over P1, if it's low like 4, compression and expansion can be done in a single centrifugal stage, saving up on turbomachinery costs. Hence, carbon dioxide is appealing while the R1234 ZEZ is not. Third is the sensitivity analysis. The cycle comes to a halt at ambient temperature, therefore the environment serves as a cold store. Thus, the environment has an impact on performance. Because the pressure ratio of the turbomachinery in a system is essentially constant, the value of P2 over P1 from the design point of T0 equals to 15 degrees Celsius is utilized. The T0 ranges from 5 degrees Celsius to 35 degrees Celsius. The maximum top round trip efficiency of most fleet is unaffected by T0, which is around 1 percentage point variation overall, where this means it can be used all year round without compromising performance. Carbon dioxide is the only exception as T critical is close to T0, but it is quite sensitive to ambient circumstances. With roughly 10 points of fluctuation overall, which is a significant disadvantage. And lastly, we are going to focus on the R1311. The R1311 is the most efficient, where it has the second lowest heat to work ratio and has the average power density. Lowering the top pressure during discharge to a value of P ratio lower than 1 tends to raise the work ratio and reduce turbomachinery losses. As the output work has increased for the same input effort, the round trip efficiency improves. However, the increase is only 0.3%. The increases in top pressure during discharge with a P ratio higher than 1 value are undesirable because they lower the work ratio and thus increase turbomachinery losses. The only benefit is to reduce heat exchange losses by shifting away from the critical point, but it is less pronounced when the cycle operates at the optimal top temperature. Therefore, round trip efficiency is lower than for P ratio equals to 1. And finally, it is a conclusion. In conclusion, the provider's cycle model characterizes the storage temperature which maximizes round trip efficiency, where the Pareto fronts were used to rank fluids based on their performance in terms of high power density and low heat to work ratio. Carbon dioxide has a high power density as per expected from the literature, but has a deprived round trip efficiency than other fluids and is significantly more sensitive to ambient temperature than other fluids. Due to its low storage temperature, it also has an acceptably high heat ratio. However, this has the advantage of being able to function at temperatures that are compatible with non-pressurized water storage, which could be cost effective. Hence, only R1311 is the good compromise between performance and safety in general. More research could look into different types of storage fluids, such as high temperature molten salts, which would work well with an ammonia cycle. An economic study could further distinguish between the fluids. For example, by weighing the expense of having intermediate storage tanks versus the reduction in heat exchanger losses. The impact of ambient temperature should be examined further by separating charge and discharge to see if a day and night cycle scheduling is beneficial. This is all for me, madam. Thank you.